Alright, we're going to now look at the section on the hyperbola, which is another type of conic section. We have circles that we studied some time ago, back in the review chapter. We have ellipses, which we studied in the last section, now the hyperbola. A hyperbola, by definition, is the set of all points in a plane, all points x, y, such that the difference in distances between the points x, y and two fixed points, which are again called foci, is a positive constant. Alright, now, I've tried to draw a picture. I didn't do a great job. I tried to draw a picture of what a hyperbola might look like. And what I'm trying to show here is that you have two fixed points, and you will look at the set of all points such that this distance minus this distance is a fixed constant, which we typically call 2a. In fact, in terms of the coordinates, we would write it this way. If my center is 0, 0, and the way I've got it drawn it is, my vertices are at A0 and the opposite of A0. And my foci are at C0 and the opposite of C0. Notice, by the way, C for ellipses, A was bigger than C, but in hyperbolas, C is bigger than A. This is distance of A here, this is distance of C. So we take the absolute value, so it's always positive, and we take the difference of those two distances there in the green line segments, and we get some number 2a, which is this distance doubled. Now, unlike the circle, unlike the ellipse, the hyperbola has two pieces of it. It has a curve that kind of looks a little bit like a U shape in this case to the right and one to the left. And I try to draw it so it looked fairly symmetric to the y-axis here, because if my center is 0, 0 and my branches are what they're called, the branches open to the right or left, we would have symmetry with respect to the y-axis. Now, speaking of some of the terminology, the transverse axis is the line segment between the vertices. So in this diagram, this would be the transverse axis, this line segment right there. The center, of course, is the midpoint of the transverse axis. And, the example I have here looks like to be 0, 0. Now the conjugate axis is not drawn in here, but the conjugate axis is the line segment that goes through the center, perpendicular to the transverse axis, and the endpoints are on something that's known as the reference rectangle. Now I don't have a reference rectangle drawn here because I don't have really this set up to show you that, but I do in my next diagrams here, so I'm going to kind of point out where the conjugate axis is. So in my drawings here, I have, I'm starting again with, just like I did with ellipses, I'm starting with hyperbolas who have a center at 0, 0. They're the easiest and the most simple equations to work with. And I've got all sorts of things drawn here with some dotted lines and line segments and some curves here in black. Well, all the stuff that's dotted is not part of the graph. It just helps us to find the graph. Okay, as you can see, the dotted green lines here are asymptotes, and we know asymptotes when we graph rational functions, how they're used to be like a guideline to show how the function approaches at a particular value. What happens to the y? Does the y get really big? Does the y get really small? And so on. So we're going to use that to help us with our graphing. And the reference rectangle is drawn here in red. Now, where did the reference rectangle come from? Well, in this diagram, this is my transverse axis, and in this diagram, vertically here, this is my transverse axis. Notice here that my branches open to the right and left. Here, they open upward, downward. Those are the ones we're going to look at in this section. Now, we had a relationship with A, B, and C from the equations for A, B, and C. A having to do with the vertex, C having to do with the foci. Well, in ellipses, A squared was equal to B squared plus C squared. But in this diagram, A squared plus B squared is going to equal C squared. Remember, I said C was bigger than A. And so if I have A units to the right and A units to the left, I'm also going to look B units above and B units below. Or if I go A units above and A units below, then I'm going to look B to the right and B to the left of the centers. All right, this guy right here that goes vertical That's what I was talking about over here with the conjugate axis. This is the transverse axis, this is the conjugate axis, the line segment. Over here, it's just kind of the opposite. This is the transverse axis, and this little guy right here, that would be your conjugate axis. Okay, now, the equation of something that looks like this, of a hyperbola that looks like this, is x squared over a squared minus y squared over b squared equals 1. Now, since a squared plus b squared equals c squared, we know c is bigger than a or b, but we don't know if a is bigger than b or b is bigger than a. And that's the case. We don't know if a is bigger. You might have a bigger number with the b squared than you do with the a squared. That's okay. The key here is that the a squared is under the first term. See how it's under the first term here as well. It's just that over here the variables are switched because we have a hyperbola that opens in different directions. As you can see here, the centers are 0, 0. The vertices, a 0 opposite of a 0, but over here 0a, 0 opposite of a. Similarly with the foci. Now I didn't put the foci in here, but the foci would probably look something like, here, let's see if I, would be probably out here somewhere, or up here somewhere, because they would be on the extension, I should say, of the transverse axis in either case. It's just that C is larger. And the asymptotes, as you can see here, they go through the origin, so we know that the y-intercept is 0, 0. And notice here that the slope on this guy is b over a or b over the opposite of a. So I get two asymptotes, plus or minus b over a. Now again, the asymptotes are not part of my graph. That's why I make them dotted. But I'm going to use them when I do the graph. Same thing, I use the reference rectangle. It's not part of the graph, but it helps me to find the asymptotes, because as you can see, the asymptotes go through the opposite corners or the opposite vertices of my reference rectangle. Same thing over here. It's just that in this case the branches open upward and downward. And notice here also, because it's opening upward and downward, the asymptote of the slope's a little different. Instead of plus or minus b over a, it's a over b. That's a lot to keep track of, and that's just the simple ones. That's the ones with centers at 0, 0. So now the graph, we're going to look for key points, and we're going to look for the asymptotes, then which means, of course, we're going to look for the reference rectangle. So I have a series of steps, and we'll graph some here in the next video, but my a series of steps are to graph a hyperbola. We want to identify the center, and we want to identify the vertices. Alright, so in these diagrams, again, the center being 0, 0, that was easy. The vertices being, look for the first number, the number that's underneath the x squared or the y squared, whatever's the lead coefficient, whatever has the positive coefficient there. Alright? And a will be the distance. If it's underneath the x, it'll be the distance to the right and to the left of the center. If it's under the y, it's going to be the distance above and below the center. Okay? Then we're going to draw the reference rectangle centered at the center of the hyperbola, and the dimensions are 2a and 2b. As you can see, this is 2a and this is 2b. And we draw that in. Again, we make it dotted. We draw the asymptotes, notice dotted. We draw the asymptotes through the opposite vertices of the rectangle. Instead of having to deal with slope, we can just use that because the slope is already set. And then we are going to sketch the branches using the vertices and also using the asymptotes, because we know our graph will approach it. It won't cross it, but it will approach it. So you want to try to make it look reasonable. You're going to have to spend a little bit of time with these graphs. Use graph paper, please, and a straight edge. You know, when you're drawing out your asymptotes and stuff like that. I see way too many of you rush through your graphs. You freehand it. There's hardly any exactness to it. You're just kind of slopping something down. Sometimes I think you're just looking at decimals and you're putting it down from decimals. We don't want to do that. We want to plot the points. We want to graph our asymptotes. We want to go ahead and put in our reference rectangle as well. You can do that very lightly in pencil. You don't have to use colored pencils. You can draw your asymptotes again dotted very lightly in pencil, but when it comes to the curves, make them a little darker, make them solid, okay? And fill up the graph. Don't just, this much of it. Fill up the graph, okay? Fill up the graph. Now notice here, in some cases the branches open very wide, and in this case here the branches a little bit, they opened a little bit more narrow. That's going to happen, and that's going to also bring in the idea of something that we discussed with ellipses called eccentricity, but we'll talk about that in one of the next videos.